Okay, so today we're going to talk about collected over water. So you have a set of notes that are linked on Canvas for you. This is separate from the assignment because you need this kind of reference chart. Okay, this is also on the back of your gas laws reference chart, which I'll be talking about, but this is kind of the idea behind it. There's a quick little intro video about what it means to be collected over water that I do want you to watch as well, but I'm going to kind of explain. So this here is a picture of water in a flask, and we're trying to collect the gas over it. But what you need to understand is that some of the water vapor actually turns into gas because water, when it's heated up, becomes steam. And so that would actually be part of the pressure that was measured for the gas. So what we have to do is we have our total pressure, which is really going to be the gas plus the pressure of the water, and we're going to subtract out the pressure of the water to just get the pressure of the gas. So that's what this table is showing. So at different temperatures, the pressure of the water changes. So these are the temperatures here, and then next to it, each one is a pressure. So I'm going to be doing several examples to show you how you're going to subtract and how you're going to do that, because I just want the pressure of the gas, okay? So let's look at example 1. We're going to start off real simple. So it says zinc metal was reacted with hydrochloric acid in order to generate hydrogen gas. The gas was collected over water during the experiment. So you're going to see those words, collected over water. The pressure was 765 mmHg, and the temperature was 22 degrees Celsius. What is the pressure of the dry hydrogen gas? So we just want the pressure of the hydrogen gas. So we have our total pressure is equal to the pressure of the hydrogen plus the pressure of the water, okay, because it was collected over water. So we're going to be subtracting out the pressure of the water, okay? So our total pressure it gave us is 765 mmHg. The thing that makes this tricky is it's not going to call it a total pressure. It's just going to say the pressure when it was collected over water, but it is a total pressure, okay, is equal to the pressure of the hydrogen, which we're solving for, plus, now, the pressure of the water is going to be different depending on the temperature. So let's look up the temperature it gave us, 22 degrees Celsius. So this table is in Celsius and mmHg for the pressures, so that's what all of this assignment will be. So we're going to go until we find 22. All right, so 22 degrees Celsius is right here. Notice that's my degrees Celsius. And the pressure at 22 degrees Celsius is 19.8 mmHg. Okay, so 19.8 is what we're going to put in for the pressure of the water. Notice the pressure units match, so now I can solve for just the pressure of the hydrogen. So since hydrogen is being added, 19.8, we're going to do the opposite, which is subtract 19.8. Oops. So that's going to cancel, but I have to do it over here. And that will be my answer. So 765 minus 19.8 equals 745.2. So the pressure of the hydrogen is 745.2 mmHg. Okay, let's try another one. A sample of gas is collected over water at a pressure of 762 mmHg at 39 degrees Celsius. What is the pressure of the dry gas? So same kind of thing. This is our total. When it says collected over water, that is my total. So 762 mmHg equals my pressure of whatever the gas is, I'll just put G, plus my pressure of water. All right, so my pressure of water, we're gonna look up. It changes with the temperature. So we go back to our table. We're looking for 39 degrees Celsius. So that is right here. Notice this is your temperature in degrees Celsius. And the number this time I'm subtracting is 52.4 because that is the pressure at 39 of the water. So this is going to be 52.4 mmHg plus the pressure of the gas equals the total, 762 mmHg. All right, so same thing as before. Since it's being added, we're going to subtract 52.4 from both sides. And that will be my pressure of just the gas alone, the dry gas. So 762 minus 52.4 equals 709.6. mmHg. Okay, so that is how that works. Okay, the thing that makes this harder is that it's not all just gonna be a subtraction. Most of the time, you're gonna be given a gas that's collected over water with the combined gas law. So now I'm gonna do 2 examples to remind you how to do that. Okay, so it says 97.5 milliliters of a gas is collected over water at 36.0 degrees Celsius and 785 mmHg. What is the pressure of the dry gas at 25 degrees Celsius in a 105 milliliter container? So I'm gonna make a list of the things that I have. So this here, milliliters, remember that is a volume. So that's V1, 97.5 milliliters. All right, and then it says it's collected over water, so we are gonna have to do our little subtraction thing. We have a temperature, 36.0 degrees Celsius. So that's my T1. And then it says, and the pressure is 785 mmHg. All right, what is the pressure of the dry gas at a new temperature? So we don't know our new pressure, question mark. And then I have a new temperature, T2 equals 25.0 degrees Celsius. And then my new volume is V2, 105 milliliters. Okay, so notice our volume units match, our temperature units match, and then that means my pressure is going to be in mmHg. So this is not a normal combined gas law because it says collected over water. All right, anytime it says collected over water, remember this is the total pressure including the water. So what we're gonna do is we're gonna subtract out, remember, because here both times we ended up subtracting out the pressure. We're gonna subtract out the pressure of water at this temperature first, okay? So I'm gonna look up 36 degrees, so 44.6 mmHg is the pressure. So I'm gonna subtract 44.6 mmHg, and that will be my real, just the pressure of the gas. I do not want the total pressure. I have to subtract it out first from the original pressure because it says collected over water. So 785 minus 44.6 is 740.4 mmHg. So that's gonna be my real P1, okay? I have another problem. My temperature cannot stay in Celsius. The reason why I waited is because this table is in Celsius, so I don't wanna convert it to Fahrenheit just yet, to Kelvin. So I'm gonna add 273 to both of them, and that will be my Kelvin temperature, so I can plug it into my law. So 36.0 plus 273 equals 309 Kelvin, and then 25.0 plus 273 equals 298 Kelvin. Okay, so that's really our list of variables. So this is gonna be a little bit more complicated. All right, so the name of this law, in case you forgot, let's see. We have P, V, and T, and then P, V, and T. So which one has P, V, and T? All of them. It's gonna be this one. We haven't learned this one yet. You don't know what N is, okay? But it's gonna be this one. So that is combined gas law. So that's what we're gonna write over here, combined. And then we're gonna write the equation. Scoot this over. So P1 times V1 divided by T1 equals P2 times V2 divided by T2. All right, so now I'm gonna take all these numbers and I can plug them in. So my P1, remember after subtracting out the pressure of the water, this is my pressure of the water that we had to look up. So this is the number I'm gonna use. So 740.4 mmHg. That's my P1. My V1 is 97.5 milliliters divided by my T1 in Kelvin, which is 309 Kelvin. All right, and then that's going to equal my P2, which is unknown, times my V2, 105 milliliters, divided by my T2 in Kelvin, which is 298 Kelvin. Okay, so just like before, when we have a law that has a fraction, we're going to cross multiply and divide. Okay, so I'm gonna use different colors. So here's my brown. So I'm gonna do those. So 740.4 mmHg times 97.5 milliliters times 298 Kelvin. Okay, then I'm gonna use a different color. I'll use blue and do those three. So that's gonna be equals 309 Kelvin times P2 times 105 milliliters. Okay, so now I have everything in a straight line, and now I can solve for P2. So what's happening to P2? Parentheses here mean multiply, so it's being multiplied. So the opposite of multiply is divide. So I'm gonna divide by 309 Kelvin. The reason I'm doing that is so I can cancel it here, but if I do it there, I have to divide on this side by 309 Kelvin. All right, P2 is still not alone. It's still being multiplied by 105. So we have to divide by 105 milliliters so it can cancel. And then I'm gonna do it over here. So divide by 105 milliliters. All right, so now let's look at units. Milliliters cancel, Kelvin cancels, and I'm left with mmHg, which is a unit for pressure. All right, so to solve, you're gonna multiply the top, divide on the bottom. Okay, so 740.4 times 97.5, so you can see it, times 298 divided by 309 divided by 105. Okay, so we get an answer, so let's talk sig figs. If you look back at all your givens, not all the stuff we converted, your actual givens in the problem, this one has 3, this one has 3, 3, 3, and 3. So we're gonna put 3 in our answer. So this is gonna be 663. The 0 doesn't change the 3. So my answer is 663, and then the unit that didn't cancel is mmHg. Okay, so this assignment, I'm still gonna do one more, is gonna have some where you subtract like this, where it's real simple, and then it's gonna have combined gas law, okay? So that's not going away. So let's try another one. So this one says a 3.5 liter sample of gas is collected over water, so that's our hint that we're gonna be subtracting something out from that table, at 22.0 degrees Celsius and 745 mmHg. What volume would this gas occupy at negative 1.00 degrees Celsius and 893 mmHg? Okay, so I'm gonna make a list. So 3.54 liters is my first volume. Liters is a volume, just like milliliters is a volume. Okay, and then it says it's collected over water, and then our temperature, T1, is 22.0 degrees Celsius. Our P1, our pressure, is 745 mmHg. Remember, that's not our real P1, that's really our P total, and we're gonna be subtracting out the pressure of water in just a minute. All right, and then it says what volume would the gas occupy at negative 1, so that's my T2, negative 1.00 degrees Celsius. And then we have a P2 of 893 mmHg. And we don't know a V2, so that's my question mark this time. Because it says what volume would it occupy? Okay, so again, before we do all our conversions, let's look at our gas law reference chart. Which law involves pressure, volume, and temperature for all of it? PVT, PVT. So that's gonna be combined again. All of these are combined if they're not just subtracting like that. Okay, so this is the combined gas law. And the equation again is P1 times V1 divided by T1 equals P2 times V2 divided by T2. Okay, so make sure you're writing that down. All right, so now I'm gonna change some stuff because this here says it was collected over water, so this is not my real P1. This is my total. So I have to subtract out the vapor pressure at a temperature. So the temperature it's at, all my ones, the temperature it's at is 22.0 degrees Celsius. Okay, so let me get my reference chart here. So 22 degrees Celsius, the pressure I'm gonna subtract out is 19.8 mmHg. Okay, so 745 minus 19.8 is 725.2 mmHg. Okay, anytime it says collected over water, you're going to be subtracting out the water vapor pressure from that table. All right, our temperature cannot stay in Celsius, so we're going to add 273 to both of those. So 22.0 plus 273 is 295 Kelvin. And then -1, notice it's the negative button, 0.00 plus 273 is 272 Kelvin. Remember, Kelvin will never, ever, ever be negative, okay? So you're gonna add 273 every time. All right, so now I'm ready to plug in some stuff. Use the same colors that I did before. All right, so my P1, here's my law. My P1 from my list is 725.2 mmHg. It's the number I get after taking away the water vapor pressure when it's collected over water. My V1 is 3.54 liters divided by my T1 in Kelvin, which is 295 Kelvin, equals P2, which is 893 mmHg, times my V2, which is unknown, divided by my T2 in Kelvin, which is 272 Kelvin. So just like before, anytime I have a fraction, I'm going to cross multiply and divide. So I'm going to start with this brown. So I'm going to do these three first. Reminder, on the combined gas law, it will always be 3 numbers on top and 2 numbers on bottom that you're dividing. And it's going to be the same way again. So I'm going to rewrite those. 725.2 mmHg times 3.54 liters times 272 Kelvin. Just took those 3 numbers and wrote them multiplied. The parentheses mean multiply. Equals, and then now I'm going to use blue for these 3. So that's going to be 295 Kelvin times 893 mmHg times V2. All right, so V2, remember the parentheses mean multiply. So V2 is currently being multiplied. So the opposite of multiply is to divide. So I'm going to divide by 295 Kelvin. When I do 295 divided by 295, it cancels, but I got to do it over here. So I'm dividing by 295 Kelvin. V2 is still not alone, so I'm going to divide by 893 mmHg, which is going to cancel over there, but I got to do it over here. So divided by 893 mmHg. Okay, let's look at units. mmHg cancels. They match on top and bottom. Liters doesn't cancel, but Kelvin does. So I'm left with liters, which I'm looking for V2, and that is a unit for volume. So remember to solve. You're going to multiply the top 3 and divide the bottom 2. Notice again, it's 3 numbers on top, 2 on bottom, every time for combined gas law. So 725.2, scoot that up so you can see. 725.2 times 3.54 times 272 divided by 295 divided by 893. Okay, so let's look at sig figs. All of my original givens, this one has 3, this one has 3, 3, 3, and 3. So my answer will have 3. The 0 does nothing to the 5, so the answer is 2.65 liters. Okay, so you can see that, 2.65 liters. Because all of my givens had 3. It has nothing to do with when we add or subtract or any of that stuff. So all the ones on this assignment are all collected over water, so you will be subtracting for all of them. Just some of them will have the combined gas law like this. Some of them will just be like our first 2 examples where you're just subtracting from the total. Email me with any questions.